All right, welcome back to our strange and mysterious process for taking definite integrals and getting numbers out, or definite integrals and getting a number out at the end. This new thing that we're doing. Okay, another example. This time we're integrating from a lower bound of -1 to an upper bound of +1, and our function is 6x squared minus 3. So our general antiderivative of 6x squared dx is going to be 6 times 1/3 x to the power of 3 plus c, which is 2x to the power of 3 plus c. Our antiderivative of 3 is 3x plus c. And we can hide the plus c's. So we're going to have 2x cubed minus 3x, hide the plus c's, evaluated from -1 to 1. We'll plug in the top bound. So we have 2 times 1 cubed minus 3 times 1, minus the bottom bound, 3 times -1 cubed minus 3 times, sorry, I missed a typo there, 2 times 1, -1, like that, and then simplify. So we have 2 minus 3 there, minus -2 plus 3. So the first bracket, -1, second bracket, +1. So we have -1 subtract 1, which is -2. Don't worry about that. Don't worry that this is a negative number. Yes, there is an interpretation of these answers in terms of areas under a curve. What this is telling us is that between -1 and 1, overall, there's more of the curve below the x-axis, more of the curve that has a negative y value. And those will give negative contributions to an area measurement that isn't constructed properly. So if we wanted to interpret this in terms of an area in between curves, we would have to make a modification. We have to do something. And it's not as simple as just making this +2. I'll show you when we get to that. Okay, here's another example. We want the antiderivative of 1 over x evaluated from 1 to e to the power of 3. Well, the antiderivative of 1 over x is ln absolute value of x. So ln absolute value of x evaluated from 1 to e cubed. So this will be the ln of absolute value of e to the 3 minus the ln absolute value of 1. We can drop the absolute value symbols because e to the 3 is positive and 1 is positive. And then for ln of e to the 3, use the cancellation law. Ln of 1 is 0. 3 minus 0. We get our final answer of 3. I'll write that down. Antiderivative of 1 over x dx is equal to ln absolute value of x plus c. And hide plus c since we have bounds on the integral. Just as a reminder why we're hiding the plus c. It'll cancel out. So we've been doing a few examples of integrals with and without bounds, and we've been using some properties of integrals. I want to highlight some of those properties and invite usage of them in subsequent examples. So the first property that we had previously is a property that allows us to factor a constant set of antiderivatives. So let's say you have the antiderivative of a constant c times f of x. You can bring that constant up front. So you have c times the antiderivative of f of x. Putting bounds on the integral does not change that. Second property is that if you have an antiderivative with or without bounds of two functions that are added together or subtracted from each other, you can split that up into the antiderivative of the first plus or minus the antiderivative of the second. If you change the order of the bounds, so if, let's say we're integrating from 1 to 5, we're going to get some number out of that. If we switch the order, if instead of going from 1 to 5, if we go from 5 to 1, we are going to get the negative of that answer. Here's why. This first one, if we say that the general antiderivative is capital F, then this first one is f of b minus f of a. And the second one is minus bracket f of a minus f of b. If we multiply the negative through, negative f of a minus minus plus f of b, and we're very fortunate to be working in a system where order of addition does not matter. Can you imagine if losing that? Well, what happens? It's not a very nice type of system to be working in. Anyway, so we'll exploit the fact that order of addition does not matter to say negative f of a plus f of b is f of b minus f of a. So that's why that happens. That's why when you change the order of integration, when you change the order of the bounds, a minus sign appears in front. Next property is, what if the bounds are the same? What if you're integrating from 5 to 5 or from 2 to 2? Well, what you will always get is you'll get 0. Because you get the antiderivative of the top bound minus the antiderivative of the bottom bound. Whatever it is on top minus the same thing at the bottom, you're going to get 10 minus 10, you're going to get 0. And the last property, the most interesting one, the one that we're going to use in some subsequent problems, is for splitting up an antiderivative. Taking like a pit stop. You know, like you take a road trip, let's say you go from one city to another city and you stop halfway to use the washroom. Well, that's what we're doing here with this with an antiderivative. We're integrating from A to B, but actually we're going to take a pit stop at C. We're going to stop at C, use the washroom, have something to eat, and then continue on our journey to B. Geometrically, what we would be doing in this last property is we're splitting up the area. If we're looking at the area from x equals a to x is equal to b, we could look at the area from A to C, look at the area from C to B and add them together and get the total. So I actually want to draw that in. It is a preview. Oh, you're hearing a 3-year-old right now screaming. He's remarkably quiet for a while. Okay, so what is integral from, let's say, 0 to 100 of f of x dx? We could split this up as integral from 0 to 20 of f of x dx plus an integral from 20 to 80 of f of x dx. Sorry, what am I doing? 20 to 100. We could stop at 80, take another break, and then go from 80 to 100, but I'll just keep things simple and do that here. So I'll draw a picture of what this means. Okay, so here's my function. I'll use kind of the same f of x as before. Now we're going from 0 to 100. So here's my 100. So there's my integral. And then I'll draw the same function over here. The best I can, at least. Well, that's not the best I can. I can do a little better. I am trying to make it look the same. Okay, that'll have to do. So we went, instead of going all the way from 0 to 100, we took a pit stop at 20. So this is the first area. That's this part. And then we added the second part. We went from 20 to 100 here. And the sum is the same. Green area is equal to orange area plus the purple area. So that's a geometric reason for why that property is true. We can just split up our calculation into two calculations and add them together. Sometimes this is extremely important. Here's an example that's artificial. It's just like what we did in the last thing. We have an integral from 0 to 100 is equal to two things added together. So here we're told what that integral is equal to. We're told that that area is equal to 20. So the integral from 0 to 100 of f of x dx is equal to 20. And we know that the integral from 75 to 100 is 12. And the integral from 0 to 75 is unknown. What is it? What is the unknown quantity? So the way I'm going to solve this is I'm going to write down that the integral from 0 to 100 of f of x dx is equal to integral from 0 to 75 of f of x dx plus the integral from 75 to 100 of f of x dx. And then I'm going to put down what do we know? What are our knowns? So we're told that this first one is 20. The second one is unknown. And this third one, from 75 to 100, is 12. We can rearrange. So 20 minus 12 is equal to the integral from 0 to 75 of f of x dx. So the answer is 20 minus 12, 8. That's it. And yeah, this is the test style example. Here's another one. This one's a little bit more complicated. We have some more manipulation to do. We're asked for this one. This is what we want. We want the integral from 5 to 7. So let's see if we can find the biggest one and express our knowns in terms of that. We have integral from 2 to 7 of f of x dx is equal to, oh, there's a 3. Took the 3 out front. Use that property of integrals, bring the constant out front. 3 times that integral is equal to 27. I can divide both sides by 3. So integral from 2 to 7 of f of x dx is equal to 9. Then the next part, we have 2 times the integral from 2 to 5 of f of x dx is equal to 6. Divide both sides by 2. So 2 to 5 integral f of x dx is equal to 6 over 2, which is 3. Now we want 5 times the integral from 5 to 7 of f of x dx. So I'm just rewriting the information that we have. You'll see why I'm rewriting it in this way in a moment. Kind of converting everything into common units is one way to think about this. Getting rid of all the constants as much as possible. Now I look at the biggest range. I have a 2 to 7, a 2 to 5, and a 5 to 7. So my largest range is a 2 to 7. I'm going to express the other ones in terms of that. My integral from 2 to 7 of f of x dx can be written as an integral from 2 to 5 of f of x dx plus the integral from 5 to 7 of f of x dx. I have some knowns I can plug in. I have 2 to 7 integrated is 9. I have 2 to 5 integrated is 3. So 9 is equal to 3 plus the unknown. It tells us what the unknown is. We're not quite done though. We're not able to declare victory. The answer is not 6. It's not what we want yet. So 6 is equal to the integral from 5 to 7 of f of x dx. And now we can make a conclusion. Thus, 5 times the integral that we have, 5 times the integral from 5 to 7 of f of x dx is equal to 5 times 6. Is equal to 30. And that's our answer. So what this hinged on was using that property. Using that property to, or using two properties. One property that allows us to factor a constant out of an integral, and the other property that allows us to split an integral up into parts. The next example is much nastier. We don't have constants to fiddle with, but we have a different issue. We want the integral from 50 to 70. What we don't have is a nice split. We have an integral from 0 to 100. We're told that that integral is 90. We have an integral from 0 to 70. We're told that that's 10. And we have an integral from 50 to 100, and we're told that that's 5. Can we find what the integral from 50 to 70 is? So I'm going to draw a picture for this one. This one calls for a picture. Okay, and then we're gonna write down our special points. 50, 70, and 100 are our special points. 50, 70, and 100. So integral from 0 to 100 of f of x dx is equal to, I can go from 0 to 70 plus integral from 70 to 100 of f of x dx. And if I sketch out what that looks like, that's breaking it here, breaking at that point. But the problem is I do have 0 to 70, but I don't have 70 to 100. So I gotta think of a different way to split this based on the information that was given to me. So I'm gonna split it into plus the integral. Well, what do I have? I have integral from 50 to 100 of f of x dx. What's that going to do? So let's sketch both of those. Integral from 0 to 70 is this area here. So that's that region. Integral from 0 to 70. And then I have an integral from 50 to 100. So I'll color that differently. So I'll use red. To 100. And look at that region in the middle that we're double counting. We are double counting the integral from 50 to 70. This is double counted. So we need to subtract it. We need to subtract one of it. So minus integral from 50 to 70 of f of x dx. Here's another way you could think about this. Let's say this integral is telling us how much money has been earned. So from time 0 to time 100, $90 was earned. From time 0 to 70, $10 is earned. From time 50 to time 100, $5 is earned. We've double counted the earnings from 50 to 70. Those earnings have been claimed in two different regions. We can figure out how much has been double claimed if we know what the total is supposed to be. So I'm going to plug in our knowns. I have 90 here for the whole thing. From 0 to 70, I have 10. From 50 to 100, I have 5. And I have my one unknown, which I'm just going to keep there, minus integral from 50 to 70 of f of x dx. So 90 is equal to 10 plus 5 minus that. So 90 is equal to 15 minus the unknown. Subtract 15 from both sides. So 75 is equal to negative of what we want. And that means what we want is negative. So the integral from 50 to 70 of f of x dx is equal to negative 75. You can see that there's a homework problem like this in the worksheet. Yes, it is interesting. Yes, it is somewhat confusing. But it's one of the techniques that's used to merge information. If you have overlaps, you don't want to double count things. You need to subtract how much has been double counted, subtract it once, so it's only single counted. And we'll take a break here and continue in another video because it's a slightly different topic.